Jonathan showed. And the very first sentence of the abstract said, the purpose of this calculus was to reason about design and requirements of time-critical systems. That's the purpose. Now, there are many techniques which have evolved which talk about model checking, reasoning, about designs, their verification, but the requirement is still very thin. And while there are software model checkers and there are hardware model checkers, very little available in case tools which directly works with refinement. So this is part of unfinished agenda, as far as I see. Now, duration calculus was ahead of its time, as was mentioned, I think, by Anders. It plunged into this technology of specifying refinement right then. And if I have to summarize it in one line, I would say it is an interval temporal logic which gives quantitative constraints on accumulated duration of propositions which are measured in time intervals. And I'll elaborate a little bit. Okay. Time is a major parameter against which evolution of systems is studied in physics, in electrical engineering, and in computer science. Of course, the notion of times differ. The most natural notion of time in physics, electrical engineering, and embedded systems, real-time systems, is that it is real value. So it sometimes goes by the name continuous time. And in duration, system state evolves with time, and so a behavior is nothing but something like a timing diagram. For each observable proposition in the system, it fixes the value of the proposition at each time point. Okay. In duration calculus, it was assumed that behavior is finitely variable. It changes only finitely often in any finite interval because it takes energy to change state. Very crazy things don't happen in real life. Okay. For simplicity, I'll assume that behaviors are right continuous. There are answers. Okay. Right continuous behavior, I'll assume behaviors are right continuous. There are no glitches. This is just for simplicity. Okay. But there are other notions of time. For example, instead of plotting the behavior again for all real numbers, we could sample the behavior at a few points. So behavior would be a sequence of states together with the timestamps. And it is assumed that between two such observations, nothing interesting has happened. So the state persists between them. And this view gives us what is called the timed words or time state sequences. It's a very prominent model of time behaviors. And there is a very well developed theory of automata, which works from such models. The timed and hybrid automata all recognize such words. Okay. There is also a discrete time where all these sampling points are actually natural numbered. So time is measured in let's say clock cycles or number of steps of computation, and this kind of view is very useful in describing clock circuits or synchronous systems or describing qualitative behaviors that you are only worried about sequence of state changes without measuring amount of time. They are also useful for describing the behavior of systems under approximate finite precision clocks, digital clocks, which will have a fixed granularity of precision, and you will measure everything in terms of that. And the expressive power of logics with these different forms of time, as well as their decidability properties, our ability to algorithmically reason about properties varies drastically depending on the view of time you take. Okay. So there can be different kinds, even in duration calculus work, you could formulate different duration calculi for different notions of time. And this has been done. There are various different definitions, but they don't differ that much. And it's quite possible to give a kind of generic notion of duration calculus, which I have called GDC, which is parameterized by a parameter called M. Okay. And this parameter M, by controlling that, you will get this different forms of this parameter M depends on the kind of time you want to model. And by controlling that, you will get different forms of duration calculus. So I will spend a few minutes giving you this idea about this generic duration calculus. The reason I need it is it will be very useful in transforming formulae from one form of time to another, because we have this unified framework. And then we can apply good reasoning techniques which are available with one form of time for approximate reasoning for other forms of time. That is what I want to get to today. Okay. No matter what form of time you take, we have a unified view. Behavior is just a collection of timing diagrams for each proposition. It is something like this. A time interval is a pair of real numbers b with b less than equal to e. So it specifies an observation window with respect to which you are making statements. And the shape of the logic, okay, this is a time interval, this is a time interval, this is also a degenerate point time interval. And the shape of the logic is that given a timing diagram theta and an observation interval v, ignore I for the moment, we evaluate whether formula is true or false. Right? We make statements about how the behavior looks from the point of view of that model. And some of the properties you must take is something like this. The ceiling of not p says that not p is invariantly true throughout my observation interval, which would be true of this interval b currently there. Or you could have a formula which says L is greater than 60. L denotes the length of the current interval for which you are evaluating the formula. So it's E minus B for the current interval. You are saying that the time length of the interval is greater than 60. Or you have this modality called chop, which says that the behavior in my observation interval looks like this. It can be chopped into three subintervals, three consecutive subintervals, such that not P is invariantly true in the first part, P is true in the middle part, and not P is true in the last part. So the pattern of P is not P, 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 not P. Right? So it's a very visual logic. You see, it's a very natural logic. And once you get familiar with the vocabulary, you can start, almost drawing those diagrams and many cases of those diagrams in formulae. Okay, so that's the basic vocabulary of duration calculus. So length was one of the kind of measurements you made over a given interval, the time length of the interval. The other kind of measurement that you made was duration of P. Okay, thank you. So duration of P. And given a timing diagram theta, behavior theta, and an interval B, we can evaluate the accumulated time for which P is true within it. For example, I won't give the definition. Given this interval B, we know that duration of P is 11 because it first holds for 8 time units between this and this point, and then 3 more time units here. Okay, I'm going to any technicalities here. But there is this notion of duration, and in original duration calculus, you could do first order real arithmetic over these measurements. And you could, of course, change these measurements using interval modalities. But here we are going to be rather restricted. We are only going to consider what are called threshold constraints over measurements. So we will take one of these measurements, which is either duration or length, and only compare it with an integer constant. So we have a highly simplified fragment of duration calculus. That will be sufficient for this talk, and yet rich enough for many, many properties. So we just have threshold constraints over measurements. All right. Given that, how do we account for different forms of time? And that we do by specifying a notion of subclasses of behaviors and a notion of admissible intervals. So suppose S is some subset of real numbers, our sampling points, we can form all intervals out of only these endpoints. So you can restrict the endpoints with which you form intervals. Some arbitrary subset I of intervals over real numbers may be called a set of admissible intervals. Pair I theta is called an S behavior. Okay, so behavior comes with a notion of what intervals are observable. This is the first thing that you want to put into the model. And the second thing you want to do is you want to specify the classes of I theta which are allowed for your logic, right? And that specifies this parameter M. And we can generically define this GDCM given this class of S behaviors M. Okay. So the whole point is that we evaluate formulae only over admissible intervals. And the only thing that changes in the definition of duration calculus is that in the chop modality, you are allowed to chop an admissible interval into only admissible subintervals. Okay, that's the thing. So the only extra condition is this. This allows us to model a large class of duration calculi. For example, the original duration calculus takes all possible intervals over real numbers. Okay, there is no constraint on what intervals are admissible. Every interval is admissible. And forget this restriction. Okay, this is something about syntax. So the original duration calculus had all intervals as observable and all finitely variable behaviors allowed. You could have another logic where only extended intervals are allowed. Point intervals are not admissible. Because nothing, in duration calculus anyway, you don't want to worry about glitches or point properties, and behavior is right continuous. So whatever you can say with point intervals, you can say with extended intervals. So in fact, you can reduce every formula of duration calculus to an equivalent formula of what I call pointless duration calculus, slightly unfortunate name, which in fact, the only point about it is that it can express everything. Okay, and it is only talking about extended interval. There are other forms of duration calculus where the interval span only change points within the behavior. So no in-between points are ever specified. You only talk about intervals which span time points where the state changes, and so only some sort of maximal intervals. And I've seen versions of interval logics which work with this. So we have this continuous time duration calculus, the original duration calculus with all possible intervals. This was just a curiosity. Discrete time duration calculus, can be defined as follows. A behavior is called discrete if all changes of state happen at integral time points. Behavior changes only at integer time points, at clock pulses, right? And discrete duration calculus is obtained by taking all intervals whose endpoints are also integral and where behaviors are discrete. With the simple change, you get discrete duration calculus, and I will talk about sample time duration calculus in a moment. Okay, so that is the calculus. With vocabulary like this, you can specify, many interesting properties. This was the starting example given, the gas burner. For example, you may want to state properties like this. Box here, for those of you who are new to duration calculus, says for all observation intervals in my behavior, the property in the bracket holds. And the property in the bracket says if the length of the current observation interval is at most A, then the accumulated amount of leakage of gas within that interval is at most B. So it's a kind of safety property, and I think Anders talked about that way. Now you may make some design decisions which says that a leak does not last too long and the leak is not very frequent. Between two leaks, there is at least a separation of C. Given those two design decisions, you want to say that the conclusion follows from it. You want to prove this formula G for some given constants A, B, C, D true. And this is one of the kind of reasoning that duration calculus would like to do. There was a proof system which went with duration calculus and which was used to do this. Now, why should we be interested in duration calculus for specifying real-time properties? There are these dominant market brands, linear temporal logic, and its a real-time version, metric temporal logic, or there is CTL. But I think duration calculus brings with it some unique features, and I think it's important to recount those. And the first one is that it gives a kind of structured description of behaviors. Activities span time intervals. Activities are composed of sub-activities. There are interesting temporal relationships between time intervals spanned by activities. It's the ambition of interval temporal logic to describe this. For example, making an omelette takes time. It spans this time interval. To make the omelette, you have these two sub-activities. First, you break the egg, and then you perform two activities concurrently. This is my recipe. You start singing a song, which starts exactly at the beginning of breaking of the egg. Then you break the egg. Making omelette is violent. You break, beat, fry, okay? And then you beat the egg for some sub-interval, and then you fry the egg. And singing stops exactly at the same time. That's my way of making omelette. And I'm a bad cook. So I don't always get an omelette. Sometimes I get carbon, but whenever I do an omelette, it's this. So it's one way implication. Anyway, this previous example tells you that, in giving some sort of structured description of behavior, there are these relationships. And interval temporal logic is very good at describing this. It's very visual language. Secondly, we have quantitative measurements. And these measurements are naturally associated with time intervals. The probability of proton decaying in 1 second is so much. It is type 2. It rained 3 inches in Mumbai in the last 24 hours, which happened once, and it flooded the city. So there's this time interval, 24 hours, last 24 hours, during which you make a measurement of amount of rainfall, and then you put a threshold constraint on it. So you see, measurements are naturally associated with time intervals, and you can state those in duration calculus. The result is a fairly visual and a highly expressive language, and from number of case studies, the evidence is that it's quite useful and naturally required modeling of several real-time and hybrid systems. There are these volumes of papers outside, and invite you to look at that. So good. Its original purpose was requirement modeling. I think the vocabulary is good. Reasoning is done, at least was done traditionally using a proof system, and that is, people have told me, very, very hard to use. Very often error prone. I mean, this is the difficulty. So reasoning is a bit tricky. But there is one more reason why this logic should be looked at, and that is it is very good at doing compositional verification of real-time programs. This is the design part of the original paper. And there was this slogan given by Rick Henner and Tony Hoare: programs are predicates, and if we talk about real-time programs, we can say real-time programs are duration calculus predicates. This view actually entails that we give for a given programming language its specification-oriented semantics, which is we identify the program with its strongest specification in your logic. Okay, so given for every statement S, its observable behavior is captured by a formula ds, which is the strongest set formula in your logic. Okay, not only that, if you have an assembly made out of 2 subcomponents S1 and S2 and connected with an operator which I denote by times, which could be sequential composition, could be parallel composition, could be iteration. The formula for that assembly is obtained by taking formulae for the subcomponents and connecting them up by a logical operator, which mimics the working of the programming operator. Okay. This is compositionality in the sense of Frege. Meaning of assemblies are derived from meanings of components without looking at the syntax of the component. And it is my claim that duration calculus is this also allows you to do. Now this operator works not only on programs but on specifications, and so it can be used almost like a compositional proof system. Okay, and duration calculus is particularly good at doing it. In fact, carrying this view forward, number of researchers and us also give semantics of several concurrent and real-time programming languages in this fashion. So there is the semantics of STRL, which is compositional, semantics of CSP, semantics of hybrid CSP, and using, for example, this semantics of STRL, several properties about expressive power of certain classes of operator were proved. Okay, so you can do work like that. In fact, the work goes further. Taking this view, you can also compositionally plug in architectural and scheduler specifications. Schedulers talk about accumulated amount of runtime given to components and processes, and shall use that to specify, impact of schedulers on this thing. So you see, the vocabulary is very good. Going on further, we specify behaviors of web services using this logic. So I would like to suggest that this agenda, doing compositional reasoning with this logic, is also an interesting aspect of duration calculus. Enthused by all this expressive power, we have embarked upon a project in the last 3 years, which is funded by a body called BRNS in India, for heterogeneous requirement modeling and analysis. But the aim is that requirements in practice are given in very many different heterogeneous notations, and our aim is to somehow rigorously model all these heterogeneous notations and then to do some formal analysis. So what kind of notations are we interested in? Message sequence charts and its extension live sequence charts, which are part of UML2, timing diagrams. There is a version called SRTV due to Emerson and others. There are these state machines and state charts. Then WC3 consortium has standardized them into an XML syntax for these called SCXML. There are temporal logic formulas. Plus, there are all these quantitative resource and timing-oriented constraints which are naturally stated in duration calculus. And a specification consists of multiple such heterogeneous requirements. Okay. And on the project, our approach is that each requirement specifies a constraint on the behavior of the system. This constraint can also be captured within duration calculus. So we are using a variant of duration calculus which we call QDDC law. It will be used as a common notation to express all these different requirements. We'll build translators from each of these heterogeneous requirements into this logic. Okay, and then we'll perform some sort of algorithmic analysis on the resulting formula. And going ahead, we have got some prototype translators for message sequence charts, for what are called synchronous regular timing diagrams, as well as the state charts into this duration calculus like logic called QDDC law. So for example, here is a drawing tool from our tool set where you can draw message sequence charts with the regions, co-regions, and you can turn them into duration calculus formula. I don't want you to read this, but it can be done. There are other competing approaches. For example, Harel and others have also given a translation of message sequence charts into linear temporal logic, and the translation is exponential in size. We can prove that our translation is linear in the size of the diagram. So expressiveness is high. Okay. Given such a diagram, one interesting aspect is handling liveness operators, but I think for the lack of time, I'm going to skip that. Having translated all these heterogeneous requirements into a duration calculus formula or conjunction of duration calculus, what kind of analysis do we want to do? Well, first thing you want to do is check consistency of requirements, which is basically nothing but satisfiability of the resulting formula. You may even want to visualize the requirement. That is, you want to pull out certain kinds of behaviors which satisfy or violate the formula. So you want to pull out models and counter models from the formula. You want to do implication checking, as in guess-by-the case. Given some end design decisions, does a conclusion follow from that, and is this formula valid? You want to do model checking. Given a system A and a requirement phi, does the A satisfy phi? And finally, you want to do controller synthesis, which Anders Ravn very prominently also highlighted. That is, given a specification phi, where some of the variables are called input and some of the variables are called output, can you write a function f? It takes the input stream and generates output streams such that for all inputs, the specification is met. And the aim is to synthesize such a program. And we are on the project, we are tackling all of these goals. Now, in order to do that, you will require some sort of validity satisfiability analyzer for duration calculus, as well as a model checking tool for duration calculus. And that is the rest of my tool. Unfortunately, duration calculus is highly expressive, but that also makes its satisfiability and model checking undecidable. Okay, and there has been this long-standing quest for decidable fragments of duration calculus. Early on, people started working on it. There were papers by Skakebek, Sestov, Mikhail Hansen has done lots, and Zhao. Mikhail Hansen has done lots of work. Martin Franzla. These were early works. There are subsequent works by many other authors. Diertz, Danwan Hang, Zhan Naijun is going to talk about linear duration invariants. So there are many fragments of duration calculus which are decidable. And then those decision procedures have to lead to credible tools. These are the two requirements. So, for example, in the early papers, Skakebek, Sestov, and others proved that qualitative fragment of duration calculus, it does not talk about any measurements, only the interval logic part is decidable. Hansen and others, I think also Martin Franzla, showed that discrete duration calculus with only threshold constraints specifies only regular behaviors and it's decidable. Zhao and others said linear duration invariants also lead to decidable theory. I think Zhan Naijun is going to elaborate on that tomorrow. Okay, taking this second approach seriously, we can turn it into a theorem which says we can slightly extend this duration calculus to something called quantified discrete duration calculus. the time is discrete, only integer values, state changes happen at integer points, and you are allowed to quantify over propositions, which vary with time. For each formula of QDDC, we can effectively construct a finite state automaton which specifies exactly the same, which recognizes exactly the same set of behaviors as specified by the formula. There's an equivalence between formula and the automaton. And there is in fact a converse theorem that every regular language can be specified using QDDC, but not without this quantification. Okay, so this is very similar to Bucchi-Algott theorem of 60s, which says monadic second order logic exactly has similar properties. We have it for this. In fact, an easy way of doing this is by translating into monadic second order logic, which is what we did. We took this theorem seriously and implemented it. We built a model checker called DC valid. It takes a formula and constructs an automaton for it. So here is an example. This is the textual syntax for the formula. It says that initially P is true in the behavior, and the total length of the behavior is 4 steps. So you can see all paths which lead to the final state have got exactly 4 arrows. And initially, of course, all accepting paths start with the first bit 1. Okay, and Q should be true exactly at 2 points within the path. So you can see all accepting paths will make the second bit true exactly twice. Okay. This Q does not count the value of Q at the last point of the behavior. It's the technicality, how we measure the count of P. It ignores the last state, which is why this is not gain. Okay. So in some given formula like this, you can synthesize and draw such automata automatically. That is what DC valid does. This automata can be used as synchronous observers for various things, for model checking, for runtime checking, for testing. You can do many things with it. Now, of course, if you naively construct this automata, they blow up in your face, and many techniques are used. There is an excellent tool which works with monadic second order logic called Mona, which is a very nice DFA library. We make of that library. It does a BDD based representation of automata with maybe 50. My time is running. Yeah. I'll be done. Yeah. So the tool constructs automata like this, and in a series of papers, we investigated the applicability and optimizations behind these tools. And so discrete time duration calculus is decidable. Okay. And so second half of my talk was supposed to be how to change dense time formula. Can I show one slide and close?
Minus one slide.
Yes, just one slide. So I will choose which one. Okay, this one. At least this has a catchy title on discretely being dense. And the approach is that we have these various forms of time, dense, sampled, discrete, and the decidability properties, our abilities to algorithmically analyze logic very drastically depending on the kind of time you have. For discrete time, it is decidable, and we have this tool DC valid. So the approach we give to model checking dense time duration, continuous time duration calculus, that we transform the behavior from one form of time to another. That is, we approximate continuous time behavior by sampling it at all change points and maybe say all integral points and a little bit of oversampling. So we can turn continuous time behavior into an approximate sample time behavior carrying sufficient information. It's an approximation. And this sample time behavior has arbitrary timestamps. We can digitize those to nearby integers. So we can get an approximate discrete time behavior. And we can do similar transformations on formulae so that the formulae preserve satisfaction under these morphisms. So we can approximate continuous time formulae by discrete time formulae, which either preserve models or counter models, and if you're lucky, both. And if I want to keep it as close as the original space. So we have some transformations, and we have built those, and that allows us to model check discrete continuous duration calculus. So that's all I wanted to say today. I don't believe that. Yeah. Okay, thank you very much.
I'm afraid we don't have time for questions. I'm going to use a very long last sentence, but there's lots of, okay.
You reduce your decidability to reachability in an automata.
Yes, that is for discrete
So
time.
the other cases is there also the decidability reduced to reachability in an automata?
Which case?
In these other cases,
Continuous time?
yeah, in the other.
Sample,
other-
yes, sample time and other. Unfortunately, there are not strong automata theoretic characterizations of continuous time logics or sample time logics. There are fragments for which such things happen. So our approach is not to approximate it by an automaton which over approximates the class of behavior or under approximate. So we mount the validity of the class of models of the formula by automata which either over approximate or under approximate the class of models. And
might it be that the decidability question might run towards the question of decidability of elementary theory of real numbers?
Why don't you guys do that during the dinner? I'm going to nominate both of you to sit together because we have to talk about some infinite state machines right now.